So today I'm going to give you, I didn't really know the audience that I would be facing. So some of the stuff that I may be talking you may already know, and other stuff may be too much, but hopefully you'll at least pick up something. I'd like to give you a little bit of my personal view of how this deep learning neural network technology has changed over a period of a few decades, as Andy was mentioning. So let's start with a little bit of history. And in this case, both artificial intelligence and machine learning. When I go and talk to people, they say, well, so what's the difference? And they're actually very similar in some cases. Like one way that I like to say artificial intelligence to people, in my neighbor that may be a doctor or a lawyer that doesn't know much about technologies, things that are very easy for people to do. Like you can see a known face and you can just recognize them right away. And as opposed to machine intelligence, I ask you to multiply two numbers, 15 digits each. Well, you learn how to do that, but 15 digits, you probably can make a mistake. You'll sweat a little bit. And yet, for the computer, it's like, no problem. So that's the machine intelligence versus the artificial intelligence in things that are easy for us. And now the problem that that has is that it's easy for us. How come this damn stupid machine cannot do it, right? And that's been the way for many, many decades. So let's start with a little bit of history. This is like back in 1950, Alan Turing creating this Turing test to propose what intelligence is. And maybe later on in 55, there was this workshop in Dartmouth College. And they figure out these well-known people say, hey, we're going to crack this up like pretty quickly, maybe a summer, maybe a couple of years. Well, they were kind of optimistic. But there was some progress made. This is one of the first artificial intelligence programs that was built by Arthur Samuel at IBM in the 50s. You can see that here. Then there was ELIZA, which is, in some case, the precursor of Siri and others. And it was amazing what it could do at that time. And because of that, the expectations were really inflated. Say, oh, if you can do this, and I know that you're just paraphrasing what I say, so how do you feel? Why do you ask me that? But it's just really not intelligence. But if you can already do that in 1966, this is not going to be too long until we crack the problem, right? In fact, Stanley Kubrick visited Bell Labs in the 60s and was starting to create science fiction movies. And he said, well, I will talk to these guys to anticipate what's coming. And he already saw the first speech synthesizers, the first speech recognizers, just very rudimentary. And said, well, fast forward, I think in 2001, this is done. Well, actually, he got one thing wrong. Not only that it's not done in 2001, it's not even done today, but the machine HAL was huge. Now, the computers are much smaller, much more powerful. So he didn't get that wrong in the other direction. And then the AI winner came. And for many years, especially AI and machine learning, like if you say that you were doing AI, they would look at you and say, what the heck are you doing? So I was in the late 80s. I saw the winner because, especially in the neural network part, the more traditional machine learning, more probabilistic and graphical models, that was doing fine. But I was doing my thesis at CMU in the late 80s. And my office mate was doing something on neural networks. And OK, that's fine. So I graduated, and he still was there. So I would come once in a while to visit my former advisor and say hi. He was still there. And then I come the following year, he was still there. Finally, eventually, he graduated. And I said, you know what? I'm not going to touch neural networks. This is not good. So I saw the winner firsthand. But there was a renaissance in the late 90s. This is one of the examples that started to popularize the world. A machine that can beat the world champion of chess. We take it for granted now, but back then, wow. I saw one of the people that worked at IBM on this was actually a professor at CMU and then moved to IBM. So I saw some of the early prototypes. So I wasn't as surprised. But other people said, oh, my God, you can do that. The machines can really think. So the expectations started to skyrocket. Stanford had this challenge, the DARPA Grand Challenge, and a car could drive by itself for a number of miles in the desert. It's like, wow, this is really coming. And then deep learning, the term deep learning has been going on for a number of years, but it hadn't really caught up very much. And I like to at least attribute this paper, science paper that Jeff Hinton did in 2006, as one of the milestones where if you look at the number of citations of the appearance of that term in the papers, it started to go up. So it's not like deep learning was born at that time, but that's one point where it was an inflection point. I will tell you what is that was in this particular paper a little bit later. And then, of course, Jeopardy. When we can beat a computer that can beat the champions of Jeopardy, that was even more impressive than chess, because here you really need to be a person. I mean, and that was really, so the expectations kept going up. Siri came up at that year. Until then, when I would talk to my neighbors, again, that were not into technology, and they tell me, so what do you do? I would say, well, I work on speech recognition. Speech what? So I tried to explain while we're having the glass of wine, and they said, well, oh, so when the machine talks, no, that's speech synthesis. Speech recognition, speech synthesis. And the guy stops thinking, I got it. The other day, my internet wasn't working. So I called the internet company to complain. And instead of talking to a person, I talked to this stupid machine that didn't understand. Is that what you do? And say, OK, you want to drink some more? So for many years, this was just an academic pursuit because it wasn't really practical. And yes, there were a few applications out there, but they were only working when they were very, very constrained. And when people tried to make it less constrained and they faced a regular user that was not the guy that knew how the system worked and knew how to do the demos and knew how to work, it just basically fell apart. But this is the time where it achieved mainstream. Mainstream, not in the sense that it's a solved problem, because it's not, in the sense that people knew what the technology was. You didn't need to say speech recognition, you didn't know what to explain. They knew, oh, Siri, I get it. And yeah, it works sometimes, some other times it doesn't work. So it was a big milestone too. I mentioned the Turing test before. There was a competition that was done by a entrepreneur that was trying to come up with, like, the Lebner Prize was called, trying to come up with a competition to see if someone could build a chatbot that would pass the Turing test. And in 2014, it did pass it according to the definition, because it fooled more than 30% of the judges. The idea is that you, as a judge, start typing through a chat interface, and then you see responses back, and someone needs to decide, am I talking to a person or am I talking to a computer? And 30% of the time, they fooled the judges. They thought they were talking to a computer, but not a person, but it was actually this computer. Interestingly enough, this chatbot was called Eugene Guzman, which was supposed to be a 14-year-old Ukrainian. And that was not just random. That was done by design. 14-year-old, so that you cannot expect that knows everything in the world. So you ask a question, doesn't quite answer it right, hey, it's a 14-year-old. Ukrainian, well, it's not a native speaker of English. So sometimes the grammar is not right, doesn't quite understand. So that made it easier, right? But that was still quite an interesting milestone. And more recently, Google DeepMind had AlphaGo that I don't think people were as impressed, because most people in the US don't know what Go is. So, okay, you win at that. Okay, fine, I don't even know what it is. But the program is really very difficult. So it is like a big achievement. So this is kind of like a brief history. Yes?
Well, before McCarthy died, two floors up, he actually said that game-playing computers and self-driving cars were not AI. I mean, he was very disappointed by the progress of the field at that point in time.
Yes, yeah, and this is an area where the expectations are so high, because we're just thinking we're talking to a person. And we imitate some aspects of that, but it's not really doing the same thing. From a surface, it may look like you're talking to a human, like this chatbot, but it's not. And it just fools you with the constraint of just having a chatbot, a chat conversation for 5 minutes. There's a lot more work to do. So I hope that we have some students in the room that are going to work on this and trying to solve the problems, because there are many, and I will hopefully show you some of them. So let's go into a little bit of the description of what machine learning is, which is similar to AI, but not quite. Machine learning is kind of like, as I would tell some of my friends, fancy math that is used to solve some of these problems. It's a special type of math. AI probably is more than just machine learning in that sense. And there were a couple of definitions that at least I like, back from Arthur Samuel at IBM back in the 50s. It tells you is the study that gives the computer's ability to learn without being explicitly programmed, like as opposed to a rule-based system where if the system doesn't do something correctly, You just write, if this happens, then do that, and you write more rules, and hopefully you can solve the problem. And so here, no, you don't need to write code when you do that. It's only you give me some data, and the system has the program that will learn how to improve. A more mathematical description Tom Mitchell gave is, you have a task T, and you want to define a performance metric, P. And based on experience E or some data, you want to measure improvements. By the way, every time that I see a picture, I still chuckle, like the machine learning. But what is examples of machine learning problems? Well, one of them is, and this is one that was worked on in the 90s when email started to take off, spam messages came up. So is this email message spam or is it legitimate? That's the task, that's the job that you're trying to do. And the metric is the percentage of emails that are correctly classified. It is spam, and yes, in fact, it's spam. I don't put legitimate emails in the spam folder, which, as you know, it happens sometimes. Or likewise, you get an email that is supposed to be legitimate and yet is spam. So it's not 100% even today. And then you have a database of emails with labels. Someone, in this case, is supervised learning. Someone gave you the labels, and you say, well, this is spam and this is not. So this is one example. Recognizing handwritten words is not a binary class in this case, and it's the percentage of words that are correctly recognized, and you have a database annotated in this case too. Playing checkers, we saw an example where that's the task, and it's how many times do you win, the system win, and how many times you lose. And then in this case, through reinforcement learning, your data is you can play against each other or some other games. It's not just only games that have been annotated from humans. Or in the case of automobile, you're driving in the highway using all these sensors, and how long do you travel until a human detects that there was a mistake in the autonomous car? And then you have all this data to train it. So those are some of the examples. So let's look at a little bit of math of a binary. Start with binary classification. So let's start with the example where you're trying to detect if this tumor is breast cancer or not. Is it benign or is it malignant? That's the simple question. And I only give you one feature. Like your input is the tumor size. And now you need to make a decision, classify, is this benign or malignant, just if I give you the size? Well, maybe if let's say it's a single feature, so I just plot them there. And in this case, that's the data. And that would be the decision. That's kind of like the happy case. If I do that, hey, great. And if it is on this side, I say it's a benign tumor. And if it's on the other side, it's a malignant tumor. This is what is called linearly separable. And that's, again, the happy case. In reality, life is not so good, so easy. And you cannot do that. Like if you draw just a line there, you cannot do that. And you have an error. And that's the case that is not linearly separable, which is most of the time what's going on. So what do you do in that case? You measure the errors, and you do OK most of the time, but there are all these errors. Is there something that you can do? Well, one possibility, and you have a cost function, which in this case maybe the errors. It doesn't need to be symmetric. It could be how many errors you make. It could be that making a prediction that it is benign when it's not is more costly than the other way around, because the other way around, maybe you can do another test. But in this case, so it doesn't need to be a symmetrical cost. So what you could do is, well, how about if I add more features? Maybe the tumor size and the age of the patient. Let's say that I were to do that. So now you have two-dimensional. Maybe on the tumor size, if you drew the line, yes, there are some errors. But if you have this, you could find a line for which it's linearly separable. So now I added another feature, and now the problem is linearly separable. That would be a good thing. In this case, the separation is like you have a hyperplane. In this case, there are three numbers, alpha, beta, and lambda, that you need to figure out from the trained data that will come up with that line. And that's what the learning algorithm is. And in this case, it's linearly separable. Of course, if it is not linearly separable, even after you add a couple of features, you need to add maybe more. What is the clump thickness, the uniformity of the cell size, what is this, that, and that's the game. And maybe you need to use also other classifiers. So that's just the basic, simple one. So the first, at least well-known neural network is the Perceptron back in the 50s. And in this case, the question is, how do you learn these coefficients? And Rosenblatt suggested, let's start with some random line there, and I will do iterations. And I will measure this, and I will move basically through the gradient, as we will see later. But this is the formulas that he came up with. So the first time that I saw this, I don't want to work on neural networks, not just because of my office mate is not graduating. Even before then, I said, well, I like to have a probability description or some model that I understand why we're doing this. Like this seems to work, but I didn't quite understand at that point why it was working. Therefore, I couldn't extend it. So that's one of the reasons why I was not interested in neural networks back then, because I did read some of these papers. By the way, what this would do is do one iteration based on the previous one plus the difference between what the system is producing and what the supervised label is, and times the features. And if you do that, the line will be moving until eventually it converges. And it may take several iterations. So that's the basic idea of perceptron back in the 50s. And it was a powerful technique. But also, before I go to the problem that it cannot solve nonlinear manifold problems, which of course we all know which we need the multi-layer perceptron, let me give you at least one explanation of the many ways that you can view the perceptron problem that at least I personally like, which is, since I'm coming more from the probabilistic theory point of view, can I explain this, come up with that equation looking from probability theory? Is that possible, more traditional machine learning? So imagine if I say, I want to find out the probability of H, which is going to be the output. In this case, H stands for hidden later, but in this case, just one layer. And V is the visible. And I'm going to make an assumption that is a log linear model. Basically, it's e to the linear combination of V, H, and actually the product of them. And there is like some coefficients, a vector B, a vector C, and a matrix W that I want to learn. Let's say that I have that function. We will see that if we have that, you actually can derive the previous formula. And this is how you do it. I have the conditional probability, which is what I care. What is if I know the visible vector, the observation, can I predict the probability of H? And if I use Bayes' rule, I divide this, and I can expand both components for V, both H0 and 1. In this case, it's binary variables. I replace this thing here, and you can see that I can get rid of e to the B transpose of V, goes, and you get that formula there. And moreover, now I can say, well, what happens, what is the probability of H being 1? What is the probability that the output is 1? And if you set it up, you get this, and there you go. That if you call it C plus V transpose W, that's the sigmoid, the famous sigmoid function. So that's at least, and there are many ways of deriving this, but that's the way, again, I like it because I can see, okay, now I understand why you get that. You get these numbers, you multiply them by the W's, you sum them up, you pass them through this nonlinearity with the sigmoid function, which is 0 when x goes to minus infinity and 1 when x goes to infinity. And then that's essentially the function that was used in the perceptron. So now the loss function. I want to be able to minimize errors in some form. Like I see the network produces an output. Is it a good or not? And you look at the target, and now you need to find like something that minimizes that difference in some capacity. You could do Euclidean distance, and for some applications that works. But here we're talking about outputting a probability density function. And for a probability density function, Euclidean distance is not the best distance. In fact, there are different distance measures for probability measures, but KL divergence is a popular one, or cross entropy, depends on how you look at it. So this is what we'll be using it. So I have a distribution P and a distribution Q. That formula, which is the sum of all the K values of the space of the probability measure, will give you the distance between two distributions. So this is what we'll be using. And if we have binary variables, that thing there, we don't have a laser pointer, right? No. So it is just a minus t logarithm of y minus 1 minus t logarithm of 1 minus y. That would be the difference, where y is the sigmoid function that we saw before. If you take the derivative with respect to y and you do the operations, you get that thing there. If you take the derivative of y with respect to x, just using regular derivatives, you get y times y minus y So interestingly enough, when you find the derivative of d, the divergence with respect to x is the product of these two terms. Wow, y minus c. This is the moments when I see, oh, I love math. Look at the original things, pretty complicated, lots of exponentials, and they all go away. And the derivative of that KL divergence with respect to the variable that you want is just the difference between what the system produces and the target. That's nice. Normally, when I used to take derivatives, things get much, much bigger. This is like much smaller. So that's nice. So stochastic gradient descent is the algorithm that is used to hill climb in this function. So if I have a set of coefficients, like the B, the C, and the W matrices that I come up initially, maybe randomly, and I want to come up with, I see how well the system does, and I want to hill climb and come up with a system that does better, in this case, regarding the KL divergence or cross entropy. So how would I do that? Well, what I want is I start in one place, I move in the direction of the gradient, start again, in the direction of the gradient, and so on and so forth, until I think it converges, just gradient descent. We'll see why it's called stochastic in a second. But basically, what I want is I have a set of weights, W, which are the same as W in the previous iteration, minus some constant times the gradient. And if you compute the gradient that way, using what when you saw in the previous formula, you see that you have that constant times the feature for that dimension, times the error, the difference between the target and what the system produces. And that's essentially the same formula as the perceptron. So now I've walked you through another way of getting the perceptron formula that at least personally I like, because now I say, well, you're trying to find a system that maximizes the probability of getting the right decisions. And given this particular log linear model, so you can try now different variants. You can try all kinds of different ideas, because now you understand how you can get there. It doesn't mean that this is the only way to do it. So now I show you a case of binary classification. So in many cases, that's too simple. You want to recognize n classes. In this case, what you can see is the cross entropy is expressed as you see above. And the y's is what is called softmax, which a colleague of ours, John Bridle, coined, which is essentially the output of the exponential, and you normalize by adding all of the outputs. So you take the derivative with respect to y, and in this case it's pretty simple, but the derivative of y with respect to x in this case is more complex. This is simple if y is different than j. I'll spare you the steps, but maybe you can see them. It's pretty straightforward. If it is the same, you get the y times y minus y. And when you do the derivative of d with respect to xy, you need to sum over all possible cases. Like you're trying to say, for instance, the derivative with respect to w23. It could go this way. It could go many different ways. So you need to compute all of them. It's the sum of all of them. But it turns out, guess what? Math comes to the rescue. It's the same thing as before. The difference between the target and the prediction. So even though it's pretty complicated, it still simplifies it, which is amazing, right? So the formula is the same. If you have a set of weights, the new weight at the next iteration is the previous weight times this constant times the output feature and the error, which is the difference between what you predict and what the true label is. And that's how you train it. The problem with this is that this only can solve problems that are linearly separable. And one of the reasons for the first winner of neural networks, I only talk about the second one, was discussion saying, well, even simple things like an exclusive OR cannot be learned by such a system that is linearly separable. So multilayer perceptrons came as say, well, if you stick several of them on top of each other, you can actually achieve nonlinear decision boundaries. This was initially developed in an obscure thesis at Harvard that had nothing to do with neural networks, and had a little bit of a page, well, a little bit more, by Paul Werbos in the 70s. But no one really looked at that until almost a decade later. But it turns out that that was kind of the first time that this was proposed. And the idea was more or less what we've done, just keep doing chain rule of, it was called backpropagation, but it's essentially take another derivative with respect to something, take times the derivative of that something with respect to the next one, and keep going down. So an example of how that works in this simple two-layer perceptron is you have the errors, which is the prediction, the label, the target T, and the prediction Y. In this case, the superscript 2 means is the output at the second level. And that's the derivative at this level if you want to maximize, minimize the cross entropy. Then when you backpropagate, you have this product that we saw before times the sum of all the gradients. So you're backpropagating down. And that is the formula that you can do to do the backpropagation. Just take the derivative, and now you need to sum over all of them to be able to do it. And the output, again, of, let's say, this particular weight, or one of these weights, is the same idea. You have a product of the feature at that point, like whatever input comes at that particular point, times the gradient. And that gradient is backpropagated back and forth. So that's the basic idea. And the reason it's called stochastic is that you could do this if you have m samples. Just take all of your training data, compute the gradients, move in that direction, now redo the prediction of the whole network in your training data, and do that again. But it turns out, of course, that that is very slow. You could break your training data into many small chunks called mini batches, and it turns out that you converge much faster because you can take a lot of, you need more iterations than if you take the full batch, but not many more. And because each batch is much, much smaller, maybe it's like 100 to 1,000 samples depending on the problem, and you may have millions of data points or many millions, then it could be much faster, and stochastically it will converge. So the idea is that these nonlinear networks can handle these multi-layer perceptions can handle nonlinear manifolds. Like if I give you these 2 points, and if I say, can you give me a point that is in between? Well, so probably I bet many of you would say, well, how about this one? Right? Sounds like a reasonable thing to do. But how about if I say, well, give me the points in between, but I'm going to give you a few more data points. They're this. If I give you, and I still ask you to do the middle point in between these two, you might say, oh, now in that case, I might pick that one, right? And the answer is because the correct distribution doesn't follow a linear manifold. It's a nonlinear. And that is what the power of the multi-layers is doing. It's extracting features such as you unfold this curve into something that is linear, and making the decision there is very simple. So each layer is learning features that make the linear discrimination at the end easier. That's really what this is doing. So now you learn about binary classifications, and there are many problems, that practical problems today, that can benefit from just a good binary classifier. We had in iPhones Touch ID as of a few years ago, and that's a binary program. Is this my user or is this not my user? It's a binary task. Yes, yeah, well, yes, that's really, but the problem that you're trying to solve, is that the user or not? And it could be full for many reasons, right? But that's really the task is binary. Another binary task, if it is speaker verification, is this my user or is it not? It could be a different user because you record, and it could be for many reasons. But the task is binary. Face ID, is this my user or is this not my user? Again, it could fail for a number of reasons. But they're all binary classification problems. So just the techniques that you've seen, more. Is this spam, as we discussed, or is it not spam? Am I moving the watch because I want to look at it? Is there motion detection? Because if I do this, maybe it's not motion, So it will have, like anything, it will have like a performance errors. It will make all of these things will make mistakes for different reasons, but they are binary tasks that are all of practical interest. Or is this credit card transaction fraudulent or not? But there are many other N-ary classification tasks that are also of high interest. Handwriting recognition, I see this, which number is it, which character is that? Speaker identification, which of many speakers is this? Or word prediction. So now let me give you a little bit of history, more recent history. Now deep learning and neural networks came back. I told you the 50s, I told you the 70s, but no one seemed to have used it very much until the last few years. Why is that? So speech recognition, the fundamentals of speech recognition, of modern statistical speech recognition started in the 70s. This was 1976, Fred Jelinek at IBM, who framed the problem as an information theory problem. So there is a word string, W, that the speaker has in mind. I want to say this. And now the speaker box is basically the acoustic realization of that word string, A. Now the automatic speech recognition system, ASS, is trying to invert the problem. If I observe A, can I find out W, an estimate of W? And from a information theory point of view, you want to find the W that maximizes the posterior probability of W, the word sequence, given the acoustics, which, if you use Bayes' rule, you can decompose as these two terms, or if you want to take the log, because it's more convenient, is the sum of these two components. So what are these? This is what we call the acoustic model. So if I give you a word sequence, what is the variability that I observe in the acoustic signal? And that's what we call the acoustic model. It has to do just with the fact that female speakers have a higher pitch, male speakers have a lower pitch, some speakers have this vowel in this context, all these other things. And this is the language model. It's like, how likely is it that someone is going to say this word string? And you can, by separating them, that's how a lot of the modern speech recognition systems work even today. So that's still from the 70s. Oh, by the way, this lambda thing is also something that was bothering me a lot when I started getting into the field in the 80s. Because, well, it turns out that you can get much higher accuracy by using a lambda of 0.1 or something like that. So, well, come on. Bayes' rule tells me that that should be 1. So it bothered me for many years until, of course, the modern days, people say, well, these are just features. The logarithm of P of A given W is a feature, and the logarithm of P of W is another feature. And if you build a log linear model, that's okay. So, okay. So what that says is that this model is not very good, and it's not as good as this model typically. So I'm going to give it a smaller weight. I don't trust it as much. That's in reality what we do. So let's just give you a very quick intuition of what the language model is. The language model is the probability of a word sequence. And you can just use Bayes' rule to say, well, it's probability of the first word times the probability of the second word given the first word times the probability of the third word given the first two, and so on and so forth, right? And I wasn't there, but I was told by my advisor that when Fred Jelinek proposed this in one of the meetings, he almost got shot, basically, because I said, well, are you dealing like a complex problem like language just with these numbers, these counts? Like, you must be out of your mind. So it was not caught with great applauses like at the beginning. There was quite a bit of resistance because you need to understand this. And this is very, very basic. You just count. I'll show you how the first things work. First of all, there was an approximation. So, well, I'm going to assume that it doesn't, the probability of this word only depends on the previous word or two, maybe. If it depends on the previous two, it's called a trigram. If it depends only on the previous one, it's called a bigram. Then you have foregram and so on and so forth. So it doesn't depend on the whole context. So you're making an approximation. And the second thing, how do I compute the trigram or the bigram? Well, the initial thing is I'm going to do very basic. Just use my fingers. I count how many times in my corpus I see WI-1 and WI close to each other, next to each other. And I divide it by the number of times that I see W1. And that's the maximum likelihood estimate. Now, the problem with that is if you haven't seen two words together, you're going to assign a 0 probability. That's not good. So the next thing is, well, can I, what we call do smoothing. I will take some probability mass away from this estimate and share it with the rest. I haven't seen it, but I'm not going to assume that is 0. And there were many smoothing algorithms. I will just show you one that is popular, but there are many others, good Turing smoothing, where you basically see how many times it happens, and you take some of that probability mass, if it happens 4 times, and give it to the ones that happen 3 times, and of the 3 to 2 and 1, and so on and so forth, so that you assume some non-zero probability for any sequence of words. They will have non-zero probability. They will be low, but non-zero. So that's, in a nutshell, and there's a lot more here, and just give you a very quick idea of how, yes?
If the people in the room had been familiar with autocorrect, they would have been a lot harsher in their criticism of this idea.
Right.
So acoustic models, they were using hidden Markov models. And basically what a hidden Markov model is, let's say that I take the word hot. And what I do is I decompose it into 3 phonemes. T. And each of them is modeled as a 3-state hidden Markov model. And I concatenate them. So this was described in this paper by Jim Baker in the 70s as well. He called the Dragon system. He went later to found a company called Dragon. But the name is a long story I won't tell you now. But the name of the company came from the name of his PhD thesis. And there was another paper at the same time by Fred Jelinek at IBM, and G. Baker actually went to IBM to work on this together. And the idea of a hidden Markov model is you're in one state, and you can only stay in that state in the next time or go to the next one. It's only left to right. And once you're in this, and there's some probability of staying in the state or a probability of going to the next state. And then the output probability is like, if I'm in this state, I'm going to emit a symbol that is a spectrum, let's say. And the way, what is the probability of input of emitting this or that? Well, at that point, it was mostly done with a mixture of Gaussian density functions. And that's how the acoustic models work. So it turns out that in the the late 80s and early 90s, there were speech recognition systems using neural networks. You have a couple of them. Jeff Hinton was in one of them, and Alex Weibel, and Morgan and Bourlard, and there were others. And you can see this. This was done, TDNN, time delay neural networks. There's basically some neural networks. So this is not new. And a couple of decades later, when I went to talk to these folks, I said, well, OK, so now you're using this, but isn't that what we were doing 20 years ago? What's different? Like, what happened? Interesting, right? So it turns out that there was a neural network winter for speech recognition in the 90s. All of these guys that did all this work stopped working on it. And back in 2010, things started. Why did they stop working on it? Well, so this is a curve provided by NIST and DARPA. This is years, and this is where I rate in the log scale. Notice that it's in the log scale. So the Department of Defense, DARPA, started investing quite a bit of money in the 80s in speech recognition. And the way they did it is we are going to come up with a task. We will have collections of data of people reading something. We will transcribe it, and we'll make it available to the contractors to use as training data, and then we'll give you a development set, and then we'll evaluate it on some test set that you don't see. And hopefully by doing this and just running numbers and numbers, you will hill climb and get a better and better algorithm. That was the idea. What you could see is one of the first tasks, they call it resource management. This was essentially a naval task, submarines, positions in the Pacific Ocean, things like that. But it happened to have 1,000-word vocabulary and very constrained grammar. So it's almost like the Navy talking to each other. They don't use full English. They just very regimented words. So it's a simple language model. And first, it was like the first time they ran it in 1988, it was like 20%. It was like pretty bad word error rate. Now, after you run it the first year, you say, oh, there's this other, oh, I have this idea. Oh, this doesn't work, let me try. And eventually, it went down to the single digits. And then DARPA says, well, that's an easy task now. I mean, you guys, once you go below some threshold, you're in the noise. Like 2 humans even would disagree at some point, right? So let's pick a harder task. And they pick 80s, which is, well, spontaneous. It's harder because it's not just someone reading. You're going to just have a conversation among humans that is not scripted. You don't ask you to read. Another one is read speech, also Wall Street Journal. So they brought people and said, well, go and read articles from the Wall Street Journal. And then the language is more varied. There's a lot more terms. That task had 20,000 words, many more words. And the year that they introduced it, boom, the error rate went up. People started working on it, and went down. And that's how a lot of progress in the community happened. You notice that it plateaued in the 2000s. There wasn't really much movement there. Well, so what happened is at this time, all of these neural networks for speech recognition that I mentioned were happening around here. And when Wall Street Journal came, they just could not even run the thing. So the reason why it stopped working is they were doing competitively for resource management. Wall Street Journal came and they said, well, it's 20,000 words, much more complex. And not only that, I give you a lot more data. And back then, you said, well, I can't handle. I mean, I'm running backpropagation on my little mini computer here, my sound workstation. I can't, it just doesn't run. So they just couldn't compete, and that's why it disappeared. So one of the reasons is it was not better, but it was comparable until here. But the more traditional algorithms were able to scale. You give me more data, I can run it. Yeah, it takes longer, but Moore's law was helping us. So, you could still run it. And these neural networks were already maxed out. They just couldn't do it. So that's one of the reasons for the winner. Now, there's a spring too. And I was alluding to this science paper that Jeff Hinton had in 2006. And that's essentially the idea of autoencoder and unsupervised pre-training. That's really the key aspect that fueled the renaissance, at least in my opinion, which is you have these features and you have a number of layers and you're trying to have something that can unwrap itself. So you have this bottleneck, meaning you start from a large number of vectors. In each layer you have fewer and fewer. You go to this bottleneck and then you're trying to reconstruct it. And you want something that can take the space into a low-dimensional space in this nonlinear manifold that is easy to represent everything so that you can go back and take the unrolling and reconstruct this in a compact way. And if you do that, you can do it in an unsupervised way. You can just throw all kinds of data. That was the basic idea. So there was something called deep belief networks. I was at Microsoft Research at that time. We invited Jeff Hinton to come and teach us. He was working on MNIST, which is a data set that DARPA and NIST had provided for handwritten digit recognition. And one of the people in my team, Deng, said, well, I think this is going to be it. So I'm interested. And he was in the speech team, so I'm going to work on image recognition. So, well, fortunately, I was wise enough to not tell him not to do that, but he did it. And then once he figured out how it works, so well, let's try on speech. So this paper was a first attempt on a small task. And it was a little bit better than the state of the art, but not a lot. So it was just trying to recognize phonemes. And then the next thing happened where we said, well, what happens if we try to do a large vocabulary recognition? And when they came and told me, oh, we got a 30% word array reduction in this experiment, I had never seen that. And normally I said, well, you probably have a bug. You maybe are testing on the training data or something that I didn't realize, or maybe by accident. And I said, no, it's correct. Something there. So we wrote this paper that ended up being published in 2011. And notice one thing, by the way. The previous one has deep belief networks, and this one has deep neural networks as the title. And that's because the reviewers told us, oh, we love the results, this is great stuff, but don't use DBN, that's already taken. It's dynamic Bayesian networks. Pick something else. How about deep neural networks? And so, okay. So we started using that. And deep belief networks became deep neural networks. And then, another paper on this, more elaboration. By the way, I went to Google Scholar and typed deep neural networks in quotations and see how many papers came up. This is in the log scale, by the way. So, because if you do it in the linear scale, it's like one, right? So until then, there were like, 14, 17 papers. So this is not new. People have been using the term deep neural networks before. But look what happened. It started catching on fire. Now everyone says DNS, of course, like it's part of like your regular vocabulary, right? So that's kind of interesting. So what is that we did for making this come back after? So when they asked me, why is this different than what we did in the early 90s or late 80s? So it's essentially this architecture. This is a spectrum, which is a representation of speech that has time in this dimension and frequency in this dimension. So essentially you take 20 milliseconds of audio, you take the Fourier transform, take the magnitude square, and that's what this spectrum is, and you keep doing it every time. So what this does is takes a window of speech, maybe like 20 frames, like 200 milliseconds, 100 to the left, 100 to the right, for instance, and that's your input feature. So if you have you have maybe like 800 input features because each one is like a representation of the spectrum, and you have 100 of them, right? And then we built 5 layers. And of course, 5 is because we try a number of them, and that's the one that worked best. And 1,000 neurons per layer. That was like the original system. And we had 8,000 output labels. So it's not one per phoneme, but one is per phoneme in context. Like the phoneme t would have a different output if it is in Italy than if it is in Italian, just because it's pronounced differently depending on the actual context, right? So that's why it's 8,000. And in total, there were like 12 million weights. Yes?
So the 5-layer network, these are multi-layer perceptron?
Yes.
Okay.
And then at that point, we trained it with 1,000 hours, which is way more. That's part of the reason, way more than what these guys used back in the 80s and 90s. They probably used 20 hours at most, and 5 was not unusual. So you had to put a lot of data through, because if you don't, these systems, it's very hard to get them to do better. But if you do, they scale very nicely. You add more data, boom, you add more layers. And even then, it's because of GPUs. GPUs were developed for video games. But it turns out that they're great at doing matrix multiplies. So we started using them, and that made it possible. So even with a CPU, it took a week on a GPU farm. Imagine how it would take on CPUs. Like, we'd still be waiting. And you run the first experiment, and it doesn't work the first time. So it's not just 1 week. 1 week to see, we messed up. OK, let's try this. We messed up again. And after a number of weeks, hopefully you get something right. So it's not just the 1 week, unfortunately. So that's really what happened. Well, the HMM, we have an alignment, a segmentation. So if someone tells you the word string, we do the force alignment. We say, well, we know what the HMM concatenation is. We know, because for training. We just need to find out where is the alignment, which frame belongs into which state. Once we've done that, that's the supervised label. For that frame, you have that label, and you have the spectrum. So that's the supervised information that it goes into the DNN. And that's for the output of the DNN is each of the output probabilities of each of the states in the hidden Markov model. So what was new? So algorithms. One of the differences, if you look at the neural networks in the 80s and 90s for speech, they were just outputting the probability of a phoneme, like t, and that's it. And if you do just that, it doesn't really work that much better. We model all 8,000 context-dependent variations. And they did think of that back then. It's not like they didn't. They just couldn't do it. Just the computation is just not possible. Not to mention, they may not say, well, would that even work? But that was key. That was a key thing. Now, if they had had the computation, the GPU, and the data, there's a very good chance smart people, they would have done it too, 20 years earlier. But they didn't. Unsupervised pre-training. I was alluding to the 2006 science paper by Jeff Hinton, which is like, training all these things is difficult because of the vanishing gradients. Training all these non-linear things, it can get stuck in so many non-global optima that if you get stuck there, how do you get unstuck? You're in maximum, but it's far away from the best one. So the unsupervised pre-training of doing this unrolling was like, and we thought, OK, that's key so that you can initialize and you're kind of like in the right neighborhood, and just the gradient descent will just take you just to the truly global optimum. So we use that. And deeper networks. Back then, they had only tried 3. They said, well, but you cannot tell me that the new thing is deep because now you have 5. It's just a number. Well, it does matter, right? If you could, they couldn't do it just because of computation, but you need, at least for speech, several layers deep. For other tasks, you don't. But for speech, the manifold is so nonlinear that you have to do this if you want to get results. Now, you also need more data. All of these stochastic gradient descent of optimizations, they are very data hungry. If you give it a lot of data, they will do well. If you don't, it's hard to converge. So large data and some variations in algorithms. Yes?
When you're doing the 800 input features, are you doing any sort of preprocessing, like a Fourier transform?
Yes, so we take the Fourier transform, magnitude square, and we we compute some filters. So like what is the sum of magnitude squares in this 200 hertz region? And as the frequency increases, the width of the filter increases too. So it's trying to simulate a filter bank. And then once we do that, we decorrelate this with a DCT, with a cosine transform. And that's why we get like 13 or so numbers per frame times 100. In this case, I think this system was like 20,000 words. This particular one, of course, now we have more, right? This is back 2010. That was our first experiment. Then GPUs, again, you have a lot more data, a lot more layers, a lot more computation. You have to have the GPUs. If we didn't have that, so that was like another reason. It turns out that later on, we thought this unsupervised pre-training was critical, but then we ran an experiment. It turns out that it's not. It's just that it helped us get a good solution. And now, so what happens if we take it away? It turns out if you are clever with the learning rate and all this other, there's some art there, then you don't need it. It still helps if you don't have a lot of data. This caught fire. After that, everyone was talking about DNNs, about deep learnings. A couple of years later, the image processing community started using it. Boom, totally shattered all of the ImageNet, standard databases. The error rate was just crashing down much more. One thing that I like about images is that it's easier to give some intuition about what the deep learning is doing. Like if this is your input image, if you look at what are the output neurons of the first layer doing, and you look at where they have the most activation, they're basically detecting edges. That's all they're doing. So they're extracting features that are very linear, very simple. Then the next layer is combining these features in particular combinations, and you can see that you see kind of parts of, you can see kind of like an eye, you can see a little bit of a nose. And then the last one is true faces, different faces. So what a deep network is doing is kind of like a linear system finding some features, but it's not done. It passes to the next one, which finds another set of features that linear combinations of the previous features, and so on and so forth. And once you do that, in the end, it's a nonlinear classifier. And it's quite powerful. In the case of speech, it's harder to visualize, but it's doing something similar as well. This is another example of ImageNet. So this is what we did in 2010. So what's happened in the last 7 years? Well, this is a new tool. Lots of people are starting looking at the problem and trying all kinds of combinations. And there's some new things. Well, the HMMs, the hidden Markov models, are still here. They haven't gone away, with some exceptions. The training criteria has gone from cross-entropy to MMI, sequence level. Essentially, before we're trying to say, well, is this 200 milliseconds, this T, when preceded by an A and followed by an all these things, or is it an S? It's a classifier just for this sequence. But that's not really what you want. What you want is, did I get the sentence right? And by doing sequence level optimization, you can avoid some of the independence assumptions that you're implicitly making in the cross-entropy. And that helps. That's one of the things that give you another 10 or 20% relative improvement. Features. We started with MFCC, which is the MEL frequency capsule coefficients. You ask a question on the features. We have these filter banks, and we took the DCT. And that's because when you do that, they are more uncorrelated. And that was a good thing to do back in the 80s, when if you didn't make that assumption, the Gaussian mixture densities you didn't work, because you assumed that it had to be diagonal covariance matrices. And if you had full covariance matrices, you couldn't train them. So that was helpful. But it turns out that deep neural networks, they don't care. And in fact, if you don't use it, you get slightly better results. So let's work and get, not much, but maybe 5% relative. And then there are all kinds of things that the field has done regarding training and regularization. So batch normalization, I won't go into the details. You can ask me later if you're interested. Tricks that can help you train without being an artist and say, well, is the learning rate correct? Am I initializing properly? Or doing distributed stochastic gradient descent so you can train many different machines and combine them. Things like dropout and more. So those things that have helped either converge faster or achieve a better optimal point or more. And there are many other acronyms. I won't go into it, whether it's convolutional neural networks or connection in temporal classification or convolutional long short-term memory, deep neural networks, all kinds of things. And all of them have some boost, some more. For language models, I spend most of the time talking about acoustic models because the big revolution in speech has been in acoustic models. That's where the biggest gap has been improvement. But language models have benefited from neural networks too. Often the best ones are recurrent neural networks. But because you cannot use them in the first pass, they're slow, often using the second pass. You provide a set of candidates and you rescore that. And more data. And the best thing is data. There was something that Bob Mercer at IBM said in the 80s. There is no data like more data. And that's really true. More data makes everything better, even a simple system without all the bells and whistles. And that's the number one thing that you can do. Just get a lot of data and good data. Even a simple algorithm neural network will do well. And even more GPUs. Now you have all these fancy things, you need more GPUs. So that's kind of like what the state is. I'll skip this because and there's still a lot more to do. I mean, you mentioned that we're not done, and we're definitely not done. Common sense, which is what is missing in a lot of these systems, is the least common of all senses. So adding that into computers, that's what we need to get into true AI. So I wanted to, I don't know how much more time I have, probably. So I'll give you just a quick idea of what is this good for.
Although the camera does go off, so you start telling the truth about 5:45.
Okay. So we, at least, I mean, a lot of companies are using this. That's why I hope that you're going to deep learning and machine learning, artificial intelligence. There's lots of jobs. These are a sample of the things that we are using in products. If you have an iPhone, you are using this, even though you may not know. For example, on-device recognition. It turns out that you take a picture and you want to say, well, I like wine. I go and sometimes take pictures of these bottles, and I can just type wine, and all these pictures come up, and I didn't annotate them. It happens all on your phone. So this is on-device scene recognition. It's like, oh, I didn't know that. Most people say, oh, I didn't know that. Or portrait mode. You may have seen in one of the latest iPhones where you can take this picture and it blurs the background, which is kind of like what you see with these professional cameras. Well, it turns out that it's all done digitally. We're
professional cameras. Ansel Adams would take serious issue.
Some. The good ones. Well, now you can do it in your iPhone, and essentially it's done all digitally. It's trying to say, well, is this the foreground? Is this the background? And if it is, I can apply a different blurring algorithm. Language modeling, trying to predict what is the next word. Handwriting recognition, if you want to type write into Chinese. Recommending news based on what you've watched before. And of course, Siri. So I will give you just a quick introduction to Siri. I don't know that I have a lot more slides. I'm sure we won't have time to go through it, but.
Just give them to Dennis and we could look at them in class.
So you've seen Siri in 2011. I mentioned this. And it's essentially, the idea is to have a personal assistant. Like those of us that have a real personal assistant would say, wow, what would I do now without one? Could we provide this to everybody? That's the goal, the ambition. Of course, very, very big challenge. This is the high-level architecture. You have the waveform, and the first thing you do is you pass through the ASR engine, automatic speech recognition engine, that will convert the waveform into words. Now you take these words into the natural language understanding piece that is transforming this into another space of intents, meaning, representation. And then there's a dialogue. Given what I understood, maybe I can do an action, perhaps like send a message, tell Don I'm going to be 5 minutes late, or speak back, and speak back. And that's the high-level architecture. And I'm oversimplifying, obviously, but. And then it's hooked up to many apps in many domains. You can use it hands-free. And one of the ways you can do is, hey, Siri, what is this or that? And you don't need to push a button. You can also use in dictation. Some people just like to compose messages. Phones are small. They have small keyboards. You make mistake with your thumbs. You can just push a button and dictate. And many people are using this or even get your voicemails transcribed. You get a phone call, you're in the middle of the meeting or a class, you don't want to pick it up, just let them leave a voicemail, and you don't need to go and listen. You can just see what the person said. For Apple TV, for example, you need to type all these passwords. There's no keyboard. It's kind of painful. So you can just speak the password. And by the way, this is happening just on the device. We don't want to send passwords to a server. And this is happening in many languages. Spanish, Russian, I think this is Turkish, Brazilian Portuguese, Dutch, Thai, and many more. And it happens in many devices. You probably are familiar with the iPhone and maybe iPad, but it's available in the watch. You can talk to the watch. It wasn't easy to cram a deep neural network in here, but there is one. Yes. If I have time, I will show. That's what I will show you next. It runs on the Apple TV, which, by the way, we were very happy when we saw that it got an Emmy. On the Mac, on the car, if you have one, a recent car home. So I will go into recognizing Hey Siri. Because we use this for large vocabulary speech recognition, and everyone does these days. But I wanted to just go briefly and touch one particular application, and it is, we are doing recognition here. If I say, Hey Siri, what is the weather forecast for tomorrow? I don't know, I'm connected to the Wi-Fi because there is no Wi-Fi here. Okay, that's the reason. Anyway, how does that work if you have a connection? Because all that you can do is recognize Hey Siri. That's all this thing does.
Oh, I see.
That's all it does.
Oh.
So when you set it up, you set it up and you say this a few times, and you get your watch. How does that work? So what we have is a DNN, and it's much smaller DNN than what we use for recognizing 500,000 words, which is what we use in the regular system. Because here we're only trying to recognize binary classification. Did you say Hey Siri, or did you say something else or nothing at all? So you can do much smaller. We have 5 layers too. Many layers still important, but not as fat, not as many variables. But other than that, it's simple. And we have a threshold at the end. And the trick that we do is this needs to work 24/7. Like if I put my phone here, it's listening 24/7, which means it's running this neural network all the time. Imagine the power. You don't want to run out of battery because we do that. It took us a while. And the only way we do that is because we break it into 2 pieces. So the first piece is like a special processor. Like, by the way, the latest devices have processors that are as fast as many PCs. Not all of them, but many of them. So it's incredible. But they only use that power for a very limited amount of time when you actually want it to do something. The rest of the time, it goes to several levels of sleep. And most of the time, the main processor is completely asleep. But if it's asleep, then you cannot do this. And if you were to do that, you'll burn the battery like in an hour, right? So these phones now have another processor called an always-on processor. It's never sleeping. But, of course, because there's a trade-off, it is much less powerful, right? So you can only do small number of computations if you don't want to impact the battery life. So we have a 2-layer system, similar to what a cache would do. The first one is running all the time with a very simple DNN. And then if it goes, and it's trigger happy, whenever it thinks it might be close, it says, oh, I think it might be, because it doesn't want to false reject. And whenever that happens, it wakes up the main processor and says, well, now you redo this with a bigger, fancier DNN that is more accurate. And hopefully you don't wake it up in vain many times, but you will. But it's still better than running on the main processor all the time. So that's the idea. And it's interesting that to train these systems, you need a lot of speech data, lots of GPUs, running on the lab. But actually, you can run it on the watch, the runtime. So the actual runtime, the training is painful, but the runtime is pretty fast. The one that we have on the watch is a hybrid from what I described. So the phone has the always-on processor, the small DNN, and the application processor, the big DNN that works here, the watch has only one, and it's halfway in between in computation, but it only wakes up. Now my watch is asleep. I cannot see the screen. Only when I do this, and you can see the screen, then is when it's listening, which is for a few seconds. And that's why you can do this computation all the time. So if you don't see the screen, you cannot speak. But oftentimes, if you want to say that, you don't just say, hey Siri, you say, hey Siri, and it will do that, right? So I think I have 8 minutes left, so maybe I can try to breeze through another application of deep learning beyond speech recognition, which is speech synthesis. Now this is the voice of Siri that talks back to you. And this is the component. So traditional speech synthesis back in the 50s, actually in the New York World Fair in the 30s, that was the first public demonstration. But what we call parametric synthesizers, which is a model that synthesizes. And then concatenative synthesis came in, which is what I call brute force. So I just record a bigger library of audio, and I want to stitch together chunks of audio. And if I do it properly, I can get high quality. So this is what is called concatenative synthesis. The first stage is text analysis, just trying to understand if I see a $sign, a 2, a period, and a 1 is $2.10. So doing that text analysis. Then there's the prosody generation, so that it's not a monotone, it's more lively. You need to figure out a little bit of meaning. Of course, it's not, the system doesn't understand the others, but it understands it to a limited amount. It tries to figure out if it is at the end, probably the intonation goes down, unless it's a question mark, in which it goes up. If it is a function word, probably it's not stressed, but if it is not, it's probably stressed, things like that. And then unit selection, which is the part that we use DNNs or deep learning for, and concatenate. So this is for selection of the units. So we have the speech database, we run the recognizer to align it and segment the database, and then typically we search for all possible concatenation of units such that when you put together, there's a cost function that is minimized. And the cost function has 2 components. This is the target cost. How well this particular unit matches with this phoneme that I want to realize with this prosody and all this. And the other term is this, which is the concatenation cost. If I put this together with this, does it blend well? Or is there like an ugly seam that sounds bad? And it's some kind of combination. And this is what concatenative systems have been doing for like a few decades. So if we look at the concatenation cost in particular, it's trying to minimize the Euclidean distance between the first frame of the next unit and the last frame of the previous unit. In this case, Euclidean distance. And it used a number of features, where is the F0, the pitch, or the duration, or the spectrum, MFCCs, things like this. And the target cost, it turns out that back in the early 2000s, someone developed something called hybrid synthesis, which is they come up with a parametric synthesizer that generates parameters, but instead of generating this all the way to the sample, they use it as a guide to find the units. When we started the TTS engine, we said, well, we don't want to build 2 systems to have the best system, a parametric and a concatenative. So can we cheat? And so, well, how about if instead we just use the mean, the target is just some statistics, like the mean of the phone from our trained database. Of course, that's not very good if you do just that. So, well, how about if we do this and the preceding and succeeding phone? Well, it gets better because phones change a lot in context. That's better. The problem with that is you start fragmenting your training data. Now, when you do that, you have less training data to do that. And if you keep doing that, is the death by 1,000 cuts. In fact, we wanted to add all of these features that are phoneme-based, syllable, word, phrase. I'm not going to read them. You can see them, many, many more. If you do that, then you fragment the data so much, and then it's just not going to work. So you need to be able to generalize. And that's where we came up with the idea of using a neural network. So you have all of these features as inputs, and the outputs are just the mean of the targets that you want to use. That's the basic idea. This particular network is called a mixture density networks because the outputs is just the means of a distribution. But other than that, it looks just the same as the multi-layer perceptions or DNNs that I described before. Now, we also look at the role of deltas and variances. Like, There are cases where you concatenate things, and the formants, which are like these resonant frequencies in the spectrum that you see, that you can see highlighted by these red lines, are pretty stable. So you expect that the concatenation should be this. If it is like that, that's not a good unit concatenation. So there is small delta, and they're pretty stable. But there are other times when you have diphthongs, for example, where the vowel is just changing over time, and that glides and perfectly normal. That's what you expect. So they're still smooth, but there is a non-zero delta, right? And trying to impose a zero is not natural. And there are cases where you go from a vowel to a stop or to a fricative, where there is an abrupt transition, and that's normal. That happens in speech. So we have a large delta between the two. So the fact that two units have a big discontinuity is not bad. It's expected. So can we generalize the formula before? So, well, yes. What we do is we add these terms. The terms at the bottom is the standard deviation. We measure from training data what is the deviation for that particular context. We will see that when you concatenate this vowel with this vowel, the standard deviation is very small. So any small variance is going to be highly penalized. But when you're here, you say, oh, there's a big variance. So the variance is big. It's OK. That doesn't bother. It's not something that we should be bothered with. And the same thing with the deltas in the concatenation. Sometimes you expect zero, but other times you expect something, and that's normal. So it should not be zero, the difference between the last frame of the previous unit and the first frame of the next unit. So the answer is output both the means and the variances. And that's what the network does. We did this evaluation compared to the previous version, which was done by a third party. And when we replaced it, iOS 10 to iOS 9 to 10, and this is like what we saw at that point. So hopefully you can see the difference in quality, even though reverberation. By the way, we came up with this example before the election. It was an interesting coincidence. No comment, no more comments there.
Wow.
And then just a couple of months ago, we introduced a new variant that had not only a new voice, but more fancy neural networks. And this is what the output was.
Okay, I found a few matches for dark matter available on Netflix.
Okay, I found a few matches for dark matter available on Netflix.
You can adjust the volume with your Siri remote.
You can adjust the volume with your Siri remote.
So it's a different voice, but it also has better prosody. And prosody makes it more lively. So I think that's about all the time that I have. So thank you very much. Hope they enjoyed it.